So this is the second half of section 8.2, which is hypothesis testing about a proportion. And I am wearing my, might be hard to see, my Pasadena City College shirt today, representing PCC. Even though we can't be there, it can be here. So we're looking at hypothesis testing for a proportion. Let's take a look at this example. According to NPR, which is National Public Radio, in 2016, 32.1% of adults aged 18 to 34 lived at home with their parents. A sociologist randomly surveyed recently 500 people aged 18 to 34 and found that 143 of them lived at home with their parents. At a significance level, alpha, of 0.05, do we think the proportion has changed? As always, we are using the p-value method. So remember, null and alternative hypothesis, H0, H1. Remember as well, we are testing a proportion. That's always going to be there. The first, always a statement of no change. Going to have an equal sign. But remember, this talks about the old idea. And the old idea is what happened in 2016. So we have 0.321. Then we want to know, has that proportion changed? Now, because of that wording, I don't need to check my sample evidence at this point. Just the fact that it says, has the proportion changed, tells me that this is a not equal to. Because it doesn't say, is the proportion greater, is the proportion less than. It just says changed. Another word would be is different. That's also telling you to do the not equal sign. So over here, let me just put my sample evidence, because that's what I'm using to test how strong this change is. So our X and our N, and that will create our P hat. So notice we have 143 people in the new sample that live at home out of 500. And then we can do that. We can also leave it as a fraction, or we can test it. It doesn't look like it comes out super pretty, so I'm going to write it to 3 decimal places here. So we also want to pay attention to our claim. And in this case, our claim is, do we think the proportion has changed? So this would be that the proportion has changed. So our claim is our alternative. We are trying to see, has it changed? Okay, now let's come back. And now what we have to do is we have to test that sample evidence against what used to be true. So our P, the old proportion, is 0.321. That's already a proportion. So I'm going to write Z star, that is my test statistic. And I'm going to take my sample data, the P hat, this is just from, you can look on the previous pages. I subtract it from my P, and then I'm going to divide it by the square root of, and this is a key thing because sometimes students will do this incorrectly. This is P times Q, so 0.321. And then Q is just 1 minus P. So you can either do 1 minus P, or you can just write out 1 minus. Just make sure to put that in parentheses. And then 500. And that's all under the same square root. And then a key thing to see is that if you put this all into your calculator at once, which isn't a bad idea, it will give you the most exact answer. Make sure to put the numerator either in parentheses or use your fraction bar, because if not, your calculator will give you a wrong answer because you want it to use follow order of operations. So if we do this to 2 decimal places, because it's a z-score, negative 1.68 is fine. And that's a level, again, of how strong our evidence is. So realize down here is a standard normal distribution. That's what we're looking at here, because we've just standardized our sample evidence and looked at the difference between the old idea and the new idea, the p hat minus the p, in terms of standard error, which is what your denominator is. And so we find that we're over here, and we have this in the tail here, so negative 1.68. So I should be a little bit farther over there, but this is where we're at. Now, p-value, as always. So now once I have that test statistic, it's going to help me to figure out the p-value. And here is something that students have a bit of a hard time with. But when the question just says, do we think the proportion has changed? You might say, well, look, the new proportion is less than the old proportion. So why don't we just do less than? Well, that's just not what we can do. And actually, I'll be more specific here. Let me put it the not equal to. So when we have a situation that's not equal to, and we're doing this method here with the using the tables specifically, when we do not equal, that's a two-tailed test. And so that means that our p-value is actually going to be all the area in two tails. And so our p-value, the probability that we got the sample data that we did without it actually being true data or legitimate data, becomes bigger when you just do a not equal to sign, because you're willing to accept that it's extreme in either direction. And so it just means that you're actually leaving less room for error, because you can have your significance level is only 0.05. But this is what we need to do. So we look in the table for z equaling negative 1.68, and that area is, you can look in your table, 0.0465. Okay, but that is the area right here. That is the area right here. And anytime you are doing two tails, you have to consider both tails. And so our p-value is actually going to be 0.0465 times 2. And that looks like it's going to be 0.0930. Same as before, and we'll get very used to this, we're just comparing this to our alpha, our significance level. Remember, that's the probability of a type 1 error that could be made. And I'll write it down next to my times 2 there. But you can see that this p-value is quite big, and it is bigger than 0.05. So we have this situation. And now that we have this, it allows us to make our decision. Remember from section 8.1, if the p is high, the null will fly. So what that means is, since the p-value is high, since there's a high probability that this data could have happened by chance without being legitimate data, we cannot reject the null. And that's what I'll write on the next slide. So now we're ready to make our decision. And because the p is high and the null will fly, we fail to reject H naught. Remember, only two options: reject H naught, fail to reject H naught. Always the two decisions that are possible. The conclusion that we make in this case is, when you fail to reject H naught, there isn't sufficient sample evidence to support the claim that the proportion, and then we can just reiterate the claim right from the problem, of 18 to 34-year-olds who live at home has changed since 2016. Our data, the sample data does not support it. So there isn't sufficient sample evidence to support it. So just really quickly, I'll mention that you can use your calculator to do these problems. And because these calculators can do everything. It's another test. Notice that you'll see the words test on this and one proportion. So it's a one proportion z-test because we have one proportion that we're testing against another old version. And so if you go over to test, you'll find it on these calculators, it's just number 5. And then what you'd have to put in is you'd put your, notice it'll say P naught, it'll have a little P with a 0. That is just the old idea, so 0.321 from our last problem. Notice it wants X and N, which is our data that from the sample, so 143 and 500. And then notice it gives you the 3 different options for what kind of test it is. So we want to know, is it not equal to, is our sample data not equal to the P naught? And we're going to press calculate. And notice that it gives us the z-score that we found by doing the test statistic. And it gives us the p-value that we found as well by using the table. It gives us the p-hat, which we knew because we found that too. And it tells us our n, but we already knew that. So this gives us everything. Now, if you go stat over to tests and then back down, so do it again, back down to one prop z-test, and then instead you press draw. So if you press draw, what should happen is you should see a normal distribution and you should see that the tails are shaded because it's doing exactly what we did by hand and it's showing you you know, what your p-value is in terms of the shading, just like we found. So kind of a cool thing with the test is that you can draw, and you'll see by doing the drawing what the visual representation is. So that's an option you have with your calculator. And then we now have one more. So last one. All right, so we're back to 2016. A lot apparently happened in that year. 34% of people said that it was morally acceptable to clone animals. So in 2017, a survey found that 192 out of 600 randomly selected people believed it was morally acceptable to clone animals. And so now they think the percentage may be lower than it was in 2016. Use a 0.10 significance level to test the claim that 34% of adults say that it is morally acceptable to clone animals. Use the, as always, p-value method. Okay, so null and alternative hypothesis here. Remember, based on the old idea. The old idea is that the proportion of people who believe that it's morally acceptable to clone animals is 0.34. Now, we're testing the claim that because they think the percentage now may be lower. So that's what's telling us lower. So a less than would be the idea. And then I want you to notice that in this case, it says to test, in this case, it says test the claim that 34% of adults say that it is morally acceptable to clone animals. So this here is our claim. So notice the claim is that 34%, so that it's equal to 34%. So the claim in this case is the null, and that is not as likely as being the alternative, but it could happen. And I'm going to show you the very small change that's made when we find our conclusion based on this idea. All right, so let's do our sample evidence. All right, X, and you can always pause, you know, and write it out yourself. P-hat, I have 192 over 600. That's going to be 0.32. Okay, test statistic, Z star. Remember, it is always P-hat minus your P over the square root of P times Q, which is the complement of P. So in this case, that should be 0.66, or you can just write 1 minus. Together they should make 1. And then we had 600 people, N. So if you put that all into your calculator, make sure that you can get the same number, negative 1.03. That is not a very strong test statistic. I want you to notice that when we think about putting that kind of test statistic on a standard normal distribution, and remember what this standard normal distribution represents is if that proportion were to be true, if the null were to be true and the proportion was 0.34, that's the idea of that proportion basically sitting here and being the most likely. When we look at the sampling proportion for a proportion like 0.34, the idea is this normal distribution would say if it were true that the null was correct, it's not saying you couldn't take different samples of the population and get slightly differing values than 0.34, even if 0.34 is true. And so you're trying to basically say, where is 0.32 in comparison to this, based on the idea that 600 people were surveyed. So when we get a negative 1.03, notice that's a lot of area over here. That's going to create a very large p-value, meaning the probability of getting 0.32 when in fact 0.34 is actually correct is going to be pretty high. So this is the area we need. This is our p-value. It is just a less than, so it's a one-tailed test. So it's just one number. So you can look in the tail, so negative 1.03. The area associated with that is 0. You can look it up yourself, 1515. And if you could also, of course, you could do this in the calculator. You could use inverse norm with negative you could use normal. You could use normal CDF, and you could put in, negative 1 e to the 99, and then up to negative 1.03 with a 0 and a 1, because this is the standard normal distribution. And the calculator would give you just a slightly different version, 0.1505. So they would be quite close. Okay, either one, it's not going to make a difference. But notice that's big. I mean, it's big. So in terms of the comparison, our p-value compared to alpha. So notice in alpha, they are using a fairly high significance level, meaning that the type 1 error they don't feel would be as serious as a type 2 error. And our p-value here is 0. I'll use the table, but either one is going to give you the same thing. So I would really work hard to never have you have any kind of differing decision based on the table or the calculator, because generally they are really quite close. Okay, so our p-value we see is big. The p-value is big. The p is high. The p is high, so the null will fly. We do not have sufficient sample evidence to support the idea that this new percentage is now lower. So, like we had before in the last problem, we fail to reject the null. We don't have enough evidence to support the alternative. So we fail to reject the null, always based on the null. And then the only difference between this and the last sentence is the same as before. There isn't sufficient sample evidence to. Now, here is the difference that students don't love, but when the null is the claim, the sentence is a little bit different, because we're not trying to support the alternative if our claim is the null. So instead, we use this terminology, and I'm going to put it in a different color. This is because the claim is H naught. There isn't sufficient sample evidence to warrant rejection of the claim. So instead of support the claim, we say warrant rejection of the claim, because that's our job, is to either reject or fail to reject H naught. So when the claim is H naught, it changes this part. Again, this is because claim is H naught. And we'll see this again and again, so don't get too scared. All right, warrant rejection of the claim, and then the claim is warrant rejection of the claim that less than 34% of all adults say that it is morally acceptable to clone animals. There you go. Okay. So another, the last bit of this is just the big question is always, is this statistically significant? Probably don't need that much space there, but that's the idea. So the definition of statistically significant: when observed results are unlikely under the assumption that the null hypothesis is true, and we reject the null hypothesis. So we're always looking for, is our sample data statistically significant with our basis that the null is true. We'll do more of this in 8.3 and in chapter 9, and it just keeps going.